Hello everyone, this is Meghana pursuing MTech in Civil.
Engineering department in Mahindra University, Hyderabad. Now I'm going to present my course project, that is natural frequency of street frames using PGO sensors and comparing the results with the ANSYS model under the course of infrastructural health monitoring and under the guidance of Dr. Vishalakshi Talakopula. Coming to my course project, these are the content, that is introduction, methodology, numerical modeling, experimental analysis, work to be done, and conclusion. So, going to my before going to my course project, now we have to know what is structural health monitoring. Structural health monitoring deals with the continuous monitoring of the structures. It will done by using sensors or electronic gadgets, and by this utility value can be maintained. Now, why maintenance is important? The structures such as nuclear power plants, dams, bridges, oil refineries are vital for the economic growth of the country. They ensure safety and security for the public life. They also govern the commercial market in the commercial value in the market. Further, society essentially depends on these structures for various reasons such as employment perspective, economic, life, quality upgrade, safety, etc. But unfortunately, these structures are also are also critical aging, which can result in strength degradation, quality of appearance, load capacity, and overall dependency reduction. So aging can lead to reduction in dependency, whereas society depends on all these structures. So to maintain, ensure, and continue a comfortable dependency of the structures, maintenance is important. Now, where we are heading. This structural health monitoring recognized as a crucial element of overall structural management. However, it is not part of codal requirements, but often they include in contract. So there is no detailed benefits of cost analysis and no means of certification. What are the objectives of SSM? So increase safety, detects early risks, longer span of the structures, and enhance the cost efficiency. Now coming to my project, what is the natural frequency? The natural frequency at which the frequencies at which the structure will tend to vibrate when subjected to certain external forces to vibrate when subjected to certain external forces. What are piezoelectric sensors? PZT material employs a piezoelectric effect and can be utilized to create a sensor that turns mechanical strain into electrical field, which is called as direct effect. Then it can also be employed as an actuator which has the opposite effect of converting an electrical field into a mechanical strain, which is called converse effect. These are the stages involved in the course project, that is numerical modeling in ANSYS, experimental model and analysis with PZT, and comparison of both the methods. Numerical modeling. So numerical model is developed using the ANSYS workbench tool to calculate dynamic properties, frequencies, and mode shapes. This is the experimental model analysis. Experimental model analysis is a process where the structure is described in terms of its natural dynamic characteristics such as natural frequencies, mode shapes, and damping by applying external excitation and measuring structure response at representative locations. These characteristics are important because if anything happens to structure, these parameters will definitely change. So the experimental analysis can be done in two ways. First, shaker test and impact hammer test. Now, here we are using impact hammer test because impact hammer test is a quick process compared to the shaker test. Now, what is the frequency response function? It is the ratio of the output response of a structure at a point to the force applied at the other point on a particular frequency. Both force and frequency are measured simultaneously. Response will be in the form of displacement, velocity, and acceleration. In general, FRF is a complex number consisting of real and imaginary parts. So generally, it is plotted over a frequency range. what more how we get mode shapes using frequency. So if you want the first mode shape, take first resonance peak in the FRF and join them, we'll get the first mode shape. In the similar fashion, if you want second and third mode shapes, take second and third resonance peaks and join them. And now, uh, developing a numerical model using ANSYS software. How we'll develop a numerical model using ANSYS? These are the steps involved. First is engineering data, geometry, numerical model, setup, solution, and results. So first we have to give input in engineering data, geometry, and numerical model, and these three steps automatically they update. First, engineering data. These are the material properties of the frame. Material, mild steel, Young's modulus, and Poisson's ratio, density. We have to give the input of these properties in the engineering data. Now geometry. In geometry, we have to sketch a frame using the sketch a frame of required dimensions and give a beam rectangular profile to your frame. Now, numerical model. In numerical model, first we have to generate the mesh and give the supports, fixed support at both the ends of the frame. After giving the supports, you go to solution. After giving supports, then give the total deformation and get the mode shapes. Get the mode shapes of how many mode shapes you require. You can get the mode shapes. These are the results obtained from ANSYS software. This is the first mode shape, and this is the frequency of first mode shape, that is 46.281 hertz, and second mode shape frequency is 75.606 hertz, and this is the third mode shape, whose frequency is 114.17 hertz. This is the specimen used for testing. This is the steel frame fixed at both the ends. The testing involves three procedures. One is bonding this PZT, testing this frame, and analysis. Now, how to bond the PZT to the structure? Now, by using sandpaper, remove the dust particles on the frame. By using acetone, clean the bonding site of the PZT. Now, by taking the epoxy, apply the layer of epoxy on the bonding site and bond the PZT to the structure. Where we have to bond the PZT? The PZT should be bonded at the strategic point of the structure. Now, I bonded on the center of the beam. After bonding the PZT, solder the wires, one to the positive terminal and one to the negative terminal. After soldering, apply another layer of epoxy on the PZT for protection. Bonding the PZT. Now, after bonding the PZT, another step is to test this PZT by using LCR meter. Why you have to test the PZT? Because we have to know that the PZT is working or not. So, by using LCR meter, check the PZT is working or not. Oscilloscope, we use it for the testing of this structure to get the mode shapes and natural frequencies. So, here there are two channels. Channel 1 is for response, channel 2 is for force. Channel 1 is connected to the PZT to obtain the responses, and channel 2 is connected to the impact hammer to obtain the force. So, for experimental model analysis, we use two procedures. One is shaker test and one is impact hammer test. Here we are using impact hammer test because it speed up the process of the testing. So now mark some positions on the frame to hit the frame to get the responses. So now I mark three positions. First, I'll hit on both the ends of the frame and any midpoint of the frame, midpoint of the beam. So now by using impact hammer, I'll hit the end point of the frame.
So now we are getting more response compared to force. Why? Because this weight of the hammer is more than the structure. So it is not able to take that force. So that's why we prepared our own our own hammer for this structural application. So we prepared a lightweight hammer to get our own hammer to get the responses of the structure. So now I hit one end on the beam frame, one end of the beam of a frame. So now we'll get force and response in time domain series. So the action hit the other two endpoints and obtain the data points. These data points are stored and in the form of Excel sheets and extracted. And this data is carried out for analysis.
Extract the data from the oscilloscope in the form of Excel sheets. The data will be in time domain series. So we have to convert into FFT, that is fast Fourier transformation. Then we'll get frequency domain. After getting frequency domain, we have to plot the graph between response to the force, which is nothing but FRF. From that FRF, by using peak picking method, pick the first resonance peak to get the first mode shape. In a similar fashion, pick the second and third peak, resonance peak, to get second and third mode shape. As we discussed that FRF is a complex number, we'll have absolute, real and imaginary. So we have to get the modes, first, second, third mode shapes for absolute, real and imaginary parts. These are the experimental results of absolute first mode shape, second mode shape, third mode shape. And for the real part, first mode shape, second mode shape, and third mode shape. In the similar way, real part, first, second, and third mode shape. Here, for the absolute, real, and imaginary, the first three mode shapes and the frequencies should be same. And now coming to experimental and numerical model correlation. We have to correlate the results that are obtained from experimental model and the numerical model. First, the results of the numerical model that are obtained from ANSYS software. The natural frequency of first, second and mode shapes. First mode shape is 46.661 Hz and second is 75.76 Hz. And the natural frequency of third mode shape is 114.17 Hz. In a similar way, the results obtained from the MATLAB are as follows. The results obtained from both the ANSYS and MATLAB are same and should be same. Conclusion. Natural frequencies were determined from numerical and experimental analysis, and a comparison of the results will describe the accuracy of PZT sensors for validation. Thank you.